Okay, we're going to look at section 6.4 this go around. This is the last section that we have to cover for this class. And this is just one more application that we can do. What we're going to do here is we are going to find the area of the surfaces of a revolution, okay? Now, if we were doing something, a simple shape, okay, that was like, oh, this is a cylinder, or oh, this is a sphere, things like that. We have formulas that we can do for surface area of those, okay? But the concept here is, what if I have something that is not one of our regular shapes, okay? So what if I have something, okay, so I'm going to draw just a diagram here. So I've got a part of a line, okay, and I'm going to spin this loveliness around the x-axis, okay? So what's going to happen here is, and this is certainly not drawn to scale, okay? The problem is that this is now kind of a cone-shaped thing, okay? But it's not a full cone, okay? Because I don't have the other end here. Because I can find surface areas of full cones. The question is, how do I find it when it's chopped off, okay? So I don't have a full cone here, okay? But the concept is that I could do some sort of a, it's basically, if I unwrap this, it would be kind of like a rectangle shape, okay? The problem is that I don't have, because I have a different radius here than I have here, okay? So the idea is, if I take a very, very thin strip, okay, right here in the center, and I open it up, then I have a very, very thin rectangle, okay, that if I can find the area of this rectangle and then integrate along the line, okay, then we can have this happen as we process through, okay? So the formula for this one looks kind of similar to when we did our arc length one just a second ago, okay? So the formula for this, okay, is the integral from A to B of 2 pi y, okay? Y is going to be our function, square root, okay, of 1 plus dy dx squared, okay, dx. So notice this part looks very, very similar, okay? This is when we were just doing arc length. The idea here now is I need to expand that into the revolution, so I need to find this 2 pi y part of this, okay? So we are going to look at, we're going to do the function y equals 2 square root of x, and we're going to work from 1 to 2, okay? And we're going around the x-axis. So let's get a picture here. Okay, so here's our arc. Okay. So it's kind of a bowl-shaped thing. Okay. So now let's talk about what this thing is. Now again, okay, this thing is going to be hollow, so I'm just taking that outside shell of stuff, okay? So now, looking at setting this up, okay, into our formula, kind of pulling all of our parts and pieces. A is 1, B is 2, Y is 2 square roots of x, okay? dy dx, okay? Now, excuse me. This is going to be x to the 1/2. When the 1/2 comes down, it's going to combine with the 2 to make 1, and this is going to drop. So this is x to the negative 1/2, okay? So now we're going to set this loveliness up. So we're going to integrate from 1 to 2. 2 pi 2 square roots of x, square root of 1 plus x to the negative 1/2 squared dx. Okay, well, let's play with this one, shall we? Okay. Okay, I'm going to bring these two out. Actually, I'm going to move this up. I'm just going to reset this up the top of my board. So integral from 1 to 2 of 2 pi 2 square roots of x, big square root 1 plus x to the negative 1/2 squared dx. Okay, so let me get rid of this. Okay, slide this on back up. Okay, so I'm going to bring all of this out. Okay, so I've got 4 pi sitting out here on the outside, 1 to 2, square root of x, square root of 1 plus x to the negative 1 dx. Okay, so 4 pi 1 to 2 square root of x, square root of 1 plus 1 over x dx. Okay, now I'm going to try and clean this up. 4 pi 1 to 2 square root of x, x over x plus 1 over x dx. X plus 1 over x dx. Okay, now, because I've got square root on a fraction, I can do square root of the top, square root of the bottom. Look, those cancel so nice and pretty. Okay, so I've got 4 pi integral from 1 to 2 of square root of x plus 1. Oh, I lost the dx on that last one. Okay, now guys, if I set this up as a substitution one, the derivative of this is just 1. So I'm not going to have to bring in anything like we saw in those last ones where I had like 1 plus 8x, 1 plus 9y, and I need to bring in a fraction, okay? So I've got 4 pi, and then I'm going to bracket this off, and I've got x plus 1 to the 3/2, because that's a 1/2, and then I've got a 2/3 out here in the front, evaluated from 1 to 2, okay? And that is probably not going to come out pretty at all. Okay, I'm going to bring the 2/3 out, so that's 8 pi over 3, and then I'm going to plug in the 2. So that's going to be 2 plus 1 is 3. So this is 3 to the 3/2 minus 2 to the 3/2. That's not spectacular. And playing the same trick, sorry. Move this down, okay? So I brought the 2/3 out, okay, to get my 8/3, and then I plugged in 2. 2 plus 1 is 3 to the 3/2, and then plugged in 1, and that gives me 2 to the 3/2, 8 pi over 3, and about the best I could do is maybe do this as 3 square roots of 3 minus 2 square roots of 2. Okay, that is about the best that I could hope for with that, okay? It is not a wonderful thing by any means, okay? So, but it is what it is, okay? Now, same game. If we do it in terms of x's, we always have the option to do it in terms of y, okay? We just have a slightly different formatting, okay? So we've got the integral from c to d, and usually, guys, you know that they have transitioned over the y's. when they bump to C to D's, okay, in their names, okay? So we have 2 pi x. Now remember, our equations are now in terms of y's, so this is just the function. Square root of 1 plus, I'm going to call it g prime of y squared dy, okay? Just so I've got a little bit of clarity on that one, okay? So we are going to look at the line segment x equals 1 minus y. So pretty. They've already got it in turn for me. And we're going to go from 0 to 1. And we're revolving around the y-axis, so we're in terms of what we need to be. And this is going to make a cone. Okay, so if we think about this, if I plug in 0 for y, 1 minus 0 is 1. So we are at 1, 0. If I plug in 1, okay, I get 0. So we have this line segment. We're spinning it around the y-axis. So this is going to make a lovely, wonderful cone shape, okay? Because remember that we're spinning this loveliness, okay? So we have a lovely cone. So we want to do the surface area of this, okay? So we have got the integral from 0 to 1 of 2 pi 1 minus y square root. I'm drawing out of there. 1 plus. Now, the derivative of this, okay, is going to be negative 1, okay? Nice, clean derivative. Negative 1 squared dy. Okay, so we've got the integral from 0 to 1 of 2 pi 1 minus y of square root of, now, negative 1 squared is 1, so that's going to be 2. So now, this is a constant. All of this can come out. So I've got 2 square roots of 2 pi, integral from 0 to 1 of 1 minus y dy. So 2, oops, sorry, I keep run along, forgetting to move my camera. Okay, so that's going to go to y minus 1/2 y squared, evaluated from 0 to 1. Okay, now guys, if I plug in 0, it's going to be 0. Okay, so that's going to be 0 and 0, so that's all going to go 0. So the 1 is what I care about. So at 2 square roots of 2 pi, 1 minus 1/2, so that is going to be 1/2. Okay, so we've got 2 square roots of 2 pi times 1/2. The half of the 2 will go away, so I've got square roots of 2 pi. Okay. Okay. So this is the surface area. And again, guys, for any sort of like testing purposes or anything like that, I would certainly give y'all, formulas for surface areas and arc lengths and all that kind of stuff. Like, I'm not going to leave you out tapping around because they are very, very similar. Okay. So that is the last section for that. Hopefully, if you've got any questions, do email me. Okay. And I will be more than happy to answer any sort of questions that you may have.